Well, ladies and gentlemen, today we're going to talk about the PN junction. The PN junction, one form of it is based on silicon. Here you're in the periodic table. Notice you got silicon, carbon, and germanium. Interestingly enough, our life form is organic chemistry is based on the 4 bonds you can make with carbon, and silicon, for some reason, it comes in handy for the electronics world. Alright, let's make a lattice of silicon. Now what I mean by a lattice is, of course, it's a crystal in 3 dimensions. All of it's silicon. Now they got your 4 bonds in it. To make a bond, you're basically sharing electrons. So you can do another silicon next to it. And these two, of course, we're too tiny to really, these are too tiny for our eyes to see what's going on, but in making bonds in chemistry, it's usually when you're getting a pair of electrons, 1, 2 is a pair, sharing it, and it makes the two things stick together. Alright, so I could do this in 3 dimensions somehow, but I'm on a piece of paper which is flat, so I'm just going to start drawing a bunch of these silicons, see where it gets me. Yeah, and this can just keep going for a long time. Now, in the center of the silicon are the protons. As far as we know, they kind of stay put. It's these 4 of course, silicon also has more than 4 electrons, but they're kind of tied up in the center and they're not involved in making bonds. There's only 4 of them out there that are trying to make a bond, and through the many years of studying chemistry, it seems like they want to make a bond where they get a total of 8, like the lucky 8. Chinese, the number 8's a lucky number. Well, believe it or not, in chemistry, the atoms somehow have a satisfaction point when they can call their own 8 electrons. So let's make one more road here of silicons. The little dots I'm showing is the electrons. Obviously they don't really stay put. They're spinning wildly around and get these vortex patterns that are involved, create this bonding that's going on. And by no means are these electrons staying put. That's probably how their bonding happens. They're zipping around in a certain way. But for our purposes on paper here, we're just going to show 2 side by side, which makes the linkage. So this has 4 of its own, and 4 it's kind of sharing to get a total of 8, which is seen in, because it's seen, that's how we explain the bonding. If we'd have seen something else, we'd explain it a different way. Alright, you get the idea. We're building a lattice here. I'm kind of low baud rate graphics. But, alright, let's throw in, let's make the P-type material. So let's throw in a wavered aluminum, or even a gallium, not germanium. Germanium is the alternate universe way of making a PN junction. Tin, that's too much of a metal. So these 2 fellers, and even some experimental work with carbon can make semiconductors, I think. Anyways, these are called the group 3. Is there any notification on this table, group 3? Well, let's go try to get a little story. So that's group 1. It's got 1 extra electron. It's a long way to Tipperary. I mean, it's a long way to get 8, so usually just kind of lets it loose to somebody else who, like over in this group, Fluorine Klein. They got 7 and 1 8, so to complete their Zen happiness, they just sort of need 1 more, and they just sort of take it from these guys, leaving these ionic, which means they're missing an electron. They have a plus charge. There's our calcium that's in our bones. This is group 2. It has 2 electrons, so again, oftentimes they'll lose those 2. Then this little section here is some kind of metals or something, but the electrons here are awful kind of loose. Just kind of flow, at least the outer electrons. So we kind of make a hop, 1, 2, now group 3, and then 4. So now we're back in the world where the electrons have 3 on the outside instead of 4, and this has 5 on the outside. So 3 and 5 and 4. 3 and 5, if we add these as low level, we can call them an impurity, because if everything's silicon, then anything else is considered impurity. It's just the way we think. It's just something extra added that we need, actually, so it's just something different. Alright, how can we add an aluminum? Well, let's just do it. Al. It's got some electrons, but there's only 3. 1, 2, and 3 in the bonding electrons of this little feller. Let me go ahead and draw silicon next to it. One, 2, 3, 4. There's nothing here to draw. It's missing. Let me just kind of complete the box here. Make another silicon. 4 electrons. 4 electrons. I do it, so I gotta add another silicon. 1, 2, 3, 4. Now let's add the next row. Silicon. 1, 2, 3, 4. Silicon. Of course, this is actually in 3 dimensions, so that's a little bit of a geometry lesson in going from 2 dimensions to 3 dimensions. I'll do that if I can remember how to do it. Well, there's something missing, so what's the deal? Is it just going to stay that way? Well, what happens is once these elements all get stuck together in this huge lattice, everything sort of takes on the properties of everything, and so this is missing. But what can happen is this electron, you know, these are flying around, I can kind of plop into that spot, and now the missing thing is going over here. So that's where it comes in handy to have a pencil. So, alright, I'll draw it. It moved here. And this moved over, so let's see if I can erase the ink. Alas, can I do it? Well, I guess that's why they write checks in ink, because it's hard to erase. I'll put an X marks the missing spot. I guess I could put a plus sign. Because when an electron has gone away, okay, a hole. I already drew a whole big circle, maybe a plus sign in it. Alright, what's the charge where this electron moved in? Sorry, my camera job there. So, it was neutral. It had the same number of protons balancing the electrons, but now when you added this extra electron, this aluminum now gets a minus charge. It has that extra electron, so this general area now has a minus charge. Now this thing has hopped over and taken a place and made a new bond. And now as the temperature, which means molecules moving, it bounces around, this can randomly get kicked by the temperature of moving, shaking lattice. And this can, one of these guys can then maybe move over, that's easy to see, and then this would move over there. And that would over there. And now your plus charge is roaming. It is free. Roaming around. Now, what is the odds of this? If this is in a level of 1 part per million, first let's think in 3 dimensions. If something's 1 part per million, when you do length times width times height, if you had 100 times 100, 100 times 100 is 10,000, times 100 again, I think that's 1,000,000. Let's see, 10,000, 100, yeah, 1,000,000. So, at the level of 1 part per million, you can have at the corner an aluminum atom, and you march over 100 more, you'll have another aluminum atom at the corners. Yeah, so 1 part per million sounds pretty rare, but in 3D, hopping around, it's only like 100 hops away. You know, to go from one aluminum to the next, you just have to hop 100 places. But 100 places, you're randomly hopping around, and yeah, there is a negative charge on here, so there is a slight tendency of this being drawn back. Once it gets kicked free due to the thermal vibrations, and this electron that's been kicked free and up in the air to drop into the hole, it'll in general, the electron would not want to jump there because it's repelled by that minus. It would want to jump in the other direction. So it's kind of and that would bring the hole closer and closer to the aluminum. However, going back to the lattice here, you have every outpost, every 100 spots in the corner, you got this aluminum. And let's say I've got my plus charged hole floating around somewhere in this lattice. Well, how is it now drawn? You get a minus charge here, which was created when the initial hop occurred, creating that minus charge. So every aluminum has a minus charge. And how can this find its way home? It might be slightly pulled that way, it might be slightly pulled that way by that minus charge, by that. So all these other minus charges out there will kind of randomly not end up pulling it anywhere. So unless it gets pretty close to an aluminum, it will then cancel it out and hop back in and be whole again. Sorry about the pun there. That hole will refill that bond by this electron hopping away, and then that would leave the plus charge there. So when we think in this abstract way of the plus hopping around, it's really because the minus hops to fill its space, leaving the plus one move over, like a chess piece. So yeah, this would be the P-type material. The P-type material is more locked down. You got to have that electron come free, and it usually won't come free unless it's really it's like taking the place of that hole, filling the empty bond, and then the empty bond then shifts somewhere else. With that understanding, it seems like it's less mobile. Less mobile than what? Well, let's go the other direction now. Let's talk about an impurity, which of course, actually it's the star of the show. Let's pick an impurity. Alright, there's our silicon. We'll pick phosphorus. That's got 5 electrons. It's in group 5. Let's draw phosphorus in here. So we got the aluminum here. Let's go over here and just toss in a phosphorus. P for phosphorus. Has 5. The N-type material is quite easy to explain. It has, the lattice forces onto it 4 silicons nearby it. Oops, my lattice is starting to get funky. Silicon has 4. Phosphorus has 5. I'm showing 4 here, making the bonds with the neighboring silicons, which have their 4. Oh, is my camera getting jumpy? I should have got my good camera. Alright, drawing my lattice, low speed graphics here. 4, well, it's got 5. So, yeah, there it is. I'm going to put that in a kind of bold to emphasize that there's our extra electron. Extra electron. Well, it's obviously, see, it's not really tied up in bonding. It's kind of held there because this has so many plus protons in the center of the phosphorus, and then it has so many electrons around it, but it's not well bonded other than maybe some charge attraction, and so it can kind of hop over and then just kind of be lightly bonded to some other atom in the lattice. Alright, if that leaves, this phosphorus now has a plus charge, because you have one less electron to balance. The plus charge is in the nucleus of your phosphorus. Okay, and now the thing about that extra electron is scientists have somehow observed on the electron microscope, or somehow gained evidence that not only can it hop to the next electron, next atom, it can make long hops. Like it can just sort of super scoot 20 atoms down the road and be way over, and then it lands and it kind of gets temporarily stuck on some other silicon way out there. Alright, I better end this up because my camera's acting funny, and do a part 2 of this. Now, obviously this is hopping around the lattice. What if it does, this extra electron just hop over and land where you have a plus, which means a missing electron within the bond? Well, that negative charge will simply fill that hole, and boom, everything disappears. The bond is complete, the electron goes there, and you just have, like, disappears. But not for long, because that's what semiconductors are all about, because they need the low level room temperature. I guess it's not necessarily low level, but yeah, room temperature. If you've ever seen liquid nitrogen and seen how cold that is, you can tell that kind of like as we are at room temperature compared to a turkey in the oven. Well, liquid nitrogen is like seeing us as a turkey in the oven. So we step backwards into the freezing world. Which means, okay, so if P-type material, now let's just kind of go over here. P-type material has these stationary aluminum charges, which has kind of like minus charges randomly, well not randomly, well kind of randomly strewn in. So in the mix, they somehow get them in there. I think what they do is they grow a pure crystal of silicon somehow, and then they put it in a really hot temperature and put like a gas of phosphorus, or I guess it may be some gas. You get it so hot that it's a gas of this impurity, and then it kind of wiggles its way into the lattice under such hot temperature as the atoms bang around as the gas touches the silicon crystal. You know, don't bet on that, but I think that's what it is. Alright, so with all these minus charges all around in the P-type material, alright, these are stationary minus charges. You basically have the moving plus charge, which is actually the deficiency in the bond. It's actually an electron hopping. When an electron hops, but then the plus charge moves over, so you can kind of think as the plus charge moving. However, it's all fictitious. It's actually in separate electrons hopping, but what we see is the whole moving around. In reality, it's individual electrons hop. This electron hops there, fills it. Now you got to blank that empty spot here, then another electron hops, fills it. Alright, back to the importance of these minus charges. You could not have just simply plus charges. You have to balance it with minus charges, otherwise it's kind of like electrostatic electricity. It'll very soon just pop off. What keeps those plus charges there is those stationary minus. So you actually have, for every one stationary minus charge, you've got some hopping plus charge in this P-type material. So in my picture I drew 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's draw 9 plus charges, or holes as they are known in the industry of electronics, hopping around. Alright, so while we're at it now, we're going to butt that up against, we're going to butt some P-type material. This is P-type. We're going to butt it up against some N-type. P compared to N. Alright, now N created by adding phosphorus, which has 5 electrons. Where's my phosphorus? Here we go. And what do we see? The stationary plus charge, because one of the protons is no longer canceled out by electrons, because that electron is now hopping around like a dog off a leash. Its leash broke, tasting the fine food at the neighbor's house. So instead of stationary minus charges, we're going to draw some stationary plus charges. So I guess I'm just going to draw them without circles around them. We'll just have to remember those are the stationary ones. But they do a job. They create a home for minus charges, which is now the N-type material, which is just a loose electron hopping around the lattice. We'll draw a circle around that N-type bouncing around. So I drew 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. I do 12 here. I have to draw 12 minus charges that can slide through the lattice. Oops, I almost drew a P. 1, 2, 3, 4, 5, 6. So I got 6 more to go. Oh, now you know why you have erasers. Minus, 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 minus. I'm going to get right up close. Minus. It's kind of drifting over there into next to the P-type material. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and let's add one more in this P-type material. What is that? I guess that was a plus charge. No, it had to be, I don't know what it is. 1, 2, 3, 4, 5, 6. Okay, it was a plus charge. It's a movable plus charge. Alright. We butted. So on the wafer, they soaked this side with P-type of it. They soaked this with aluminum atoms that dug into the lattice, and on the other side, they must have dug phosphorus atoms to dig into the lattice, or they somehow melted the P and N type together to fuse it at high temperature, they stick together. Alright, now I have only a few minutes left before I hit the 30-minute mark. So what happens when P and N type are getting close to each other? Well, these are randomly moving around. Now, the way you can get these to move in one direction is if you apply a voltage, which means a generalized push in one direction. So I drew this arrow, minus and plus. So minus means the electrons flow to the plus. I'm not going to get into Benjamin Franklin current, which goes the other way. It's just because he got it mixed up about the moving particles. He had to make a guess and he was wrong. So just sticking to electron current, when you put the minus charge. Now the only time these movable things is when they're kind of gently stuck to the lattice atom. They're not going anywhere. It's only when they get jostled by the room temperature movement of the atoms that they can break through. So now they're like those reaction state where it's kind of like on its own and free when it gets bumped loose from anybody. And now it can feel the whims or the gentle push in this direction. If you did apply a minus on this side and a plus on this side for your battery, that's when it can make its move. Alright, that's why it's called semiconductor, because in a metal, the electrons are like a sea of not tied down to anybody, free to move around, free agents. Once you apply a battery voltage, they just all drift in that direction. There's no need to worry about it being tied down to any particular atom. Not so in semiconductors. They're kind of tied down to the atoms, but not so much, not too much. Not too much. Alright, let's see some annihilation going on here. Fun word, which means because we are constructed stuff, everything seems to disappear. When this hops over this way, because the electron would move that way. Hold on, I guess we better reverse this. So if we put a plus and a minus, let's just do that because I feel like it. Now the electrons will drift from right to left, but the holes will drift from left to right, because if this electron, once it gets jostled and it's free agent, then it'll hop into that hole, and then the hole will then move over here. It's not there anymore. Now this electron's easy to understand. It just hops. It's still the same electron doing the hopping. And yes, lo and behold, if that electron gets too close to that hole, which is an unfilled bond, blip, it becomes part of the bonding lattice, and it vanishes. Well, at this region where you got a bunch of holes and a bunch of holes on this side, a bunch of loose electrons over here, they're moving around, and the general thing for the battery voltage is to push them to be near each other, which then gives them a chance to cancel each other out. So let me cancel one more out. The electron, the negative would push the electron this direction when it gets, when it gets jostled loose and hops into the air. And then the electron, let's say here, would hop as it, everything gets jostled and it gets loose, and then it can fall into some neighboring, very close by hole, which moves the hole here, and then it disappears here, and boom, this electron then hops here and becomes part of the bonding lattice, and now you don't see anything. There's no more moving no more moving particles. Alright, this is just about to end part one, which means when at the PN junction, at the junction where the two meet, it's called the junction, you very soon get a devouring of all the moving conductor spots. Alright, when this video shuts itself down, I'll have to start part 2. As long as I'm... Alright, I'll just start part 2. So we're going to summarize. At the junction, P and N things disappear. Oh, what the heck, it's still ticking. Alright, so this one, let's just say hopped, and one of these electrons hopped, and they got touching each other, and they disappeared into becoming the lattice. This hopped, disappeared. Now what's not disappearing are these, I'll draw them more boldly, stationary negative charges. And here, stationary, they're not moving, they're stuck. Stationary positive charges. Alright, well, let's see if I do push more electrons in this general direction. Okay, now the thing I didn't talk about is, to make this into a useful device, we have to bond, okay, this N material to metal. So without going into much detail about that, I'm just going to say you can freely lose electron and hop into the lattice as, you know, they're loose on the metal. So as the plus, you know, because there's like a quota, these stationary plus charges overall have to have the same number of moving minus charges. If you get a low amount of minus charge